Welcome to this explainer. Today we're diving into a genuine breakthrough in geometric network routing. Honestly, it sounds like something pulled straight out of a theoretical physics textbook, but it has some incredibly pragmatic, real-world implications. We're talking about taking some of the most abstract mathematical concepts, specifically high-dimensional topology, and using them to drastically slash the sheer cost and friction of computing. If you've been tracking the explosive growth in AI and routing architecture, you already know that efficiency. It's absolutely the holy grail right now.
Okay, let's dive into this. Right now, the modern computing landscape is facing a massive crisis of scale. The architectures we use to route information, especially in AI, demand staggering amounts of compute power. Seriously, every time we build a bigger model, the cost to run it just skyrockets. But what if the secret to slashing those costs wasn't about building bigger, beefier hardware, but rethinking the very shape of how data moves? What if the solution was literally hidden in abstract geometry?
So, here's our roadmap for today. We're going to cover the dense routing bottleneck, unlock angular non-uniformity, map out the Hopf vibration, dive into the sublinear compute cost reduction, and finally look at real-world scaling and trade-offs. I promise you, sticking with me through the complex topology is going to lead to a very tangible, practical payoff in hardware savings. Let's get into it.
Starting with Section 1, the dense routing bottleneck.
To really grasp the solution here, we first need to clearly understand the physical limits of our current addressing systems. Traditional AI models and high-dimensional routing networks share a pretty fatal flaw. They rely on massive, flat Euclidean parameters. Think of these like giant flat space addressing tables. And the big problem with flat space? It scales linearly. In a dense routing system, if you want to double your network capacity, you literally have to double your computational cost. Mathematically, it scales at k to the power of 1.0. This creates severe computational bottlenecks and just huge spatial crowding. The system basically chokes on its own size, because looking up routes in a massive flat table is frankly incredibly inefficient.
This brings us to Section 2, unlocking angular non-uniformity. Now this is where a major paradigm shift happens regarding how data naturally behaves when we push it into high-dimensional space. When you project token embeddings or hidden states onto a unit hypersphere, something fascinating happens. The data doesn't just spread out evenly. Instead, it shows a property called angular non-uniformity. In simple terms, the data is clumpy. It naturally clusters into preferred angular regions based on semantic similarities, leaving other regions completely empty. For a long time, this was just seen as a quirky geometric fact, but recently, engineers realized this clumpiness could actually be manipulated.
And this brilliantly illustrates how two different engineering teams can look at the exact same geometric reality and take completely opposite paths. You might have actually heard of Google's TurboQuant. Well, they saw this angular non-uniformity and decided to just destroy it. They used random orthogonal rotation to smash those clusters apart, creating independent scalars for extreme data compression. But our focus today is the complementary approach, Hopf angular routing. Instead of destroying that structure, Hopf routing exploits those natural clusters. By mapping out exactly where the data naturally wants to gather, we can create sparse, highly efficient routes that radically reduce computation. So how exactly do we exploit that structure? Let's move to Section 3, the Hopf vibration map.
This is the mathematical solution that finally replaces those clunky flat tables. But to understand it, we got to throw out the flat table entirely and start thinking in spheres. Specifically, we kick things off with a three-sphere. In this model, high-dimensional network nodes and state vectors are embedded directly onto this hypersphere. And by doing this, we can use the great circle distance to make forwarding decisions. A network packet isn't just sent to a static, rigid address anymore. Instead, it's continuously rotated toward its target along the absolute shortest geometric arc.
Let's move along and see how this builds downward. The pure brilliance of the Hopf vibration is that it projects that massive three-sphere down into a much more manageable two-sphere base space. What this projection does is isolate the global phase of the data. It gives us a coarse, global base address that dictates the primary manifold cluster where our data packet belongs. It's kind of like finding the right neighborhood before you even start looking for the specific house.
Finally, that projection leaves us with the internal structure, which maps onto a one-sphere, a localized fiber circle. Once you have your coarse base address from the two-sphere, and this is exactly where it all clicks together, the exact localized positioning and orthogonal twists of your data are defined solely by relative phase offsets on this one sphere. So your high-dimensional vector has now been uniquely decomposed into a base address and a localized fiber phase.
Now, as the signal travels and rotates across the manifold, its phase evolution is governed by a mathematical curvature field known as the Berry connection. I know, we just threw a lot of high-level topology at you, so let's ground this for a second. Why does this actually matter? Well, because this continuous phase buffering computes routes with drastically less friction. When you close the routing loop, the literal computational cost is equivalent to just a geometric phase shift. Smoother geometry literally means fewer calculations, which of course means cheaper computing.
Which brings us to the real centerpiece of our explainer. Section 4, Sublinear Compute Cost Reduction. This is where we translate all that abstract 3D stereographic geometry into hard, undeniable numbers. So the crucial point is this single number right here, 0.572. Remember how traditional flat space dense routing scales linearly at k to the power of 1.0? Well, through over 160 experimental increments, researchers proved that the routing footprint of the Hopf protocol scales sublinearly at k to the power of 0.572. Because the Hopf mechanism exploits the natural non-uniformity of the data, as the routing capacity expands, it actually occupies a decreasing fraction of the available topological cells.
And when you track the physical hardware savings across different routing budgets, the advantage of Hopf routing actually grows. At a small budget, say k equals 25, you get a modest 1.34x compute reduction. Not bad, right? But look at an extreme routing budget of k equals 5,000. A traditional dense network would require an effective footprint of 5,000. The Hopf routing footprint? Just 1,851.8. That is a massive 2.6x reduction in compute cost. By simply changing the geometric shape of the routing map, you are computing well over 2 times fewer routing paths. It's wild.
Let's move into our final section, real-world scaling and trade-offs.
We know the math works in isolation, but how does this deploy into actual hardware, and what are the honest caveats here? Well, the most immediate real-world impact of sublinear scaling is decentralization. Because the compute footprint is so drastically reduced, you don't need massive, power-hungry cluster resources to execute complex network routing and semantic mapping anymore. The Hopf protocol allows these incredibly complex operations to run locally on low-power, constrained hardware. The researchers even specifically noted that this can run beautifully on commercial silicon, like an Apple M1 processor. That is a staggering leap in accessibility. However, good science requires total transparency, which brings us to the number 8. During testing, researchers found what they called a null result when deploying this in end-to-end trainable language models. When replacing a learned gate matrix with this fixed geometric routing, they actually observed an 8% validation perplexity cost. Why? Well, because highly adaptive, gradient descent-driven layers are super fluid. If you force a rigid, pre-computed map onto them, the dynamic subnetworks simply absorb and reorganize around those topological impositions. The experts co-adapt their weights, meaning the specific geometry doesn't really yield an extra advantage in a constantly training state. But even with that 8% perplexity gap in those specific training scenarios, the overarching conclusion of the research is incredibly definitive. To quote the source directly, the R4 model is much cheaper and easier to compute. In inference or fixed routing scenarios, getting rid of a massively expensive learned gate matrix and replacing it with a fixed geometric calculation is just a monumental efficiency win. You're utilizing only a fraction of the effective expert paths compared to dense routing, natively exploiting data geometry to save raw power. Which leaves us here. We've seen how projecting data onto the 3D curves of a Hopf fibration can break the linear scaling bottleneck and literally cut computing costs by over 2.5 times at scale. It proves that the physical limitations of our hardware can often be completely bypassed by just changing the shape of our mathematics. So, I'll leave you with this. If abstract geometry can rewrite the fundamental costs of AI and networking today, what other hidden mathematical structures are just waiting to define the hardware of tomorrow? Thanks for joining me for this explainer, and keep questioning the shape of everything.